Thanks and good morning, and thank you to Terrence and Maass and Chris for the invitation to speak in this special session. So the topic of this talk is twistor spaces. So let me say a little bit about what twistor spaces are and what they do. So the idea of twistor theory is that you want to introduce complex geometry into a real geometry problem. So take a situation where there's not any apparent complex geometry there, but you introduce the complex geometry, and the way to do that is to on each tangent space to consider all of the complex structures that could act on that, and to combine them into one larger complex space. So I'll describe how to do this in the classical sense first, and then I'll look at some ways this was applied to Quaternionic spaces, and then I'll describe some recent work of mine on generalized twistor spaces. So if I just have a vector space V, a complex structure on that would be an endomorphism whose square is minus the identity. And if I have a real vector space and then a complex structure on it, then that makes it into a complex vector space in the obvious way. So if I'm looking at, say, just a two-dimensional real vector space, and usually I'm going to ask my complex structures to be compatible with the inner product and orientation. So that means that the endomorphism has to preserve lengths and has to preserve the orientation. So then on a two-dimensional vector space, there's really only one possibility. That's that you rotate by 90 degrees in the anti-clockwise direction, or in the direction compatible with the orientation. So the next step is to ask, well, what about a four-dimensional vector space? What would be all the complex structures on that? So a bit of thought reveals the following, that if I take the first vector E1, and then I ask, where does the complex structure send that? So I want it to preserve length, so it has to send it to another unit vector. Because the endomorphism squared is minus the identity, you can show that J of E1 has to be orthogonal to E1. So it has to lie inside the space, well, it has to lie in the orthogonal complement to E1, a three-dimensional vector space. Okay, so that tells you where J sends to E1, and then because J squared is minus the identity, then J sends that vector V back to minus E1. So then what about the rest of the structure? So now you can look at the two-dimensional space complementary to E1 in its image V. That's just a two-dimensional vector space, and then the complex structure there has to act by rotation by 90 degrees, and the orientation tells you in which direction, clockwise and counterclockwise. So the conclusion then is that if you want to look at all the complex structures on a four-dimensional vector space compatible with the inner product and the orientation, then they're parametrized by a two-dimensional sphere. Once you know where E1 is sent, that's sent somewhere on that two-dimensional sphere, then you know exactly what the rest of the complex structure is going to do. Right, so in twistor theory, you want to apply these ideas to, first of all, to four-dimensional real manifolds. So in this case, if you look at each tangent space is a four-dimensional vector space. The Riemannian metric is in an inner product, and you have an orientation as well. So we know that there's an S2 family of complex structures on each tangent space. So the idea of twistor theory is to take, for each tangent space, you take that S2 family. So altogether, you get a bundle of two-dimensional spheres over your four-dimensional manifold. So that's some large six-dimensional space, Z, that's fibered over the original manifold, and the fibers that S2. So Z has a natural, almost complex structure. That means on each tangent space to Z, there's a complex structure. And so it looks like this. The tangent space to Z, well, you have tangents in the fiber direction. That's in the S2 direction. And then in the sort of orthogonal direction, that orthogonal direction is just isomorphic to the tangent space of N. So, and here there's a few details that I'm just sort of skipping over. You have a Riemannian metric, so you have a Riemannian connection, and that allows you to split the tangent bundle in this way, write it as a direct sum. Okay, but in any case, the point in the sphere So x, the point where you are on the sphere, tells you what the complex structure should be on the tangent space to n. That's exactly what that sphere was parameterizing. And then in the fiber direction, S2, you can identify S2 with the complex manifold, the complex projective line. So that's naturally has a complex structure as well. So you get these you get these complex structures on each of the tangent spaces. That doesn't immediately make Z into a complex manifold. There's integrability conditions. So to be a complex manifold means that you have, at any point, you have a neighborhood that has complex coordinates, and the change of coordinates are holomorphic maps. So what I've described is just on each tangent space you have a complex structure. To actually be a complex manifold, those have to fit together in a nice way. There's some sort of integrability condition that needs to be satisfied. So in the case we're looking at, in this example, the condition for integrability of that almost complex structure is a vanishing of a curvature component of the four-dimensional manifold. And so, well, it's proved, this theorem is probably about 1980 was proved. So Tia, Hitchin, Singer proved that if the negative Weyl curvature of the four manifold vanishes, then that complex, then Z, that almost complex structure is integral, and you get a complex manifold. So the important thing here is that this problem, like looking for four-dimensional manifolds with self-dual curvature, this is a complicated non-linear partial differential equation you have to solve to find the vanishing of the curvature. But you can encode all of that in complex geometry, which is easier to understand. Okay, so just to give an example, if I take the four-dimensional sphere, then the space we get, the Z that we call the twistor space, is the complex projective space of 3 dimensions. And the map, the fibration here, you can think of, I mean, this is complex lines in C4, but each complex line generates a quaternionic line. You identify C4 with H2, and each complex line generates a quaternionic line. The quaternionic lines in H2 is, the quaternionic projective line is S4. Right, so these ideas have been generalized to, been extended to quaternionic manifolds. Now, first of all, there's 4 different kinds of, there's 4 different flavors of quaternionic manifolds. The common feature is that each tangent space is a quaternionic vector space. So on each tangent space, you have ijk that act as the quaternions on that tangent space. But then there are different cases you get depending on whether you ask for those. In each tangent space, you have the quaternionic structure. How do they fit together? If they fit together into sort of global complex structures and make the whole space into a complex manifold in 3 different ways, then you're on this row. You have either hypercomplex manifolds, or if there's also a Riemannian metric compatible with that, then we get hyperkahler manifolds. And whereas in this case, those ijk, they only extend locally, and even locally they're not integrable. So what that means is that as you move, you have ijk at one point, but as you move around, you come back in a loop, they may have get sort of interchanged. They don't extend globally. And again, you have the 2 columns where with metrics or without metrics. Okay, but once you have these ijk, at least on each tangent space, then you can look at the S2 family of all imaginary unit quaternions acting on the tangent space. So it's like AI plus bj plus ck. And so you have that S2 family of complex structures acting on each tangent space. And so again, you can combine those into this S2 bundle over your manifold M. And again, there's an integrability condition you need to check to see whether, so this twistor space Z has an actual almost complex structure, and there's an integrability condition, but it was proved by Berard, Bergerie, and Salomon that, in fact, that integrability condition is always satisfied for these quaternionic manifolds. So you get always a complex manifold in a natural way. So again, the point of this is that you have a quaternionic manifold. It has a family of complex structures, or even maybe not even complex, maybe just local, almost complex structures, this construction is a way to combine all of those into one single complex structure on this larger space, Z. Okay, so some examples. Quaternionic projective space is, you think, should be one of these kinds of Quaternionic manifolds. In fact, it's a Quaternion-Kahler manifold. It has a natural metric. It doesn't have global complex structures. It has local, almost complex structures. So, in this case, its twistor space is the projective space of dimension 2n plus 1. And the fibration is similar to the one we saw, the CP3 over S4. For hypercomplex manifolds, so that's the second row. In that case, you have these global complex structures, IJK, and the twistor space there is actually just the product of the manifold and S2. And then the complex structure on that is the complex structure on the S2 identified with the complex projected lines. And then, so you have sort of, on S2 you have the complex structure on CP1. And then in the other direction, where as you move, that's sort of parameterized by S2, the complex structure is varying in that direction. So it's combining that family of, this family of complex structures in this direction. But when you put them all together, you get a complex structure on the total space. And yeah, initially, this was the sort of the first method used to find hyperkahler manifolds. So again, hyperkahler manifolds are manifolds where the metric satisfies some complicated nonlinear partial differential equation, but you can encode all of that in this complex space, and then you can find examples by using complex geometry and algebraic geometry. Okay, so the last part of this talk, I want to talk about some of my recent work on generalized complex structures. So we've talked about complex structures. Generalized complex structures were introduced by Hitchin, and the purpose of generalized complex structures was to try to unify complex geometry and symplectic geometry. So a generalized complex structure, instead of looking at complex structures on the tangent space, you look at complex structures on the tangent space plus the cotangent space. Okay. So you have an endomorphism of Tm plus T star m, the tangent and cotangent bundle. And again, it's an endomorphism whose square is minus the identity. So if you have a usual complex structure, then that makes both Tm and the tangent and cotangent bundles into complex vector spaces. And so that's just the usual complex structure acts on Tm, and that induces a complex structure on T star. And you put those together to get a complex structure on the T plus T star. But you can do more general things than that. You can find endomorphisms that don't have that sort of mix up the tangent and cotangent bundles. So not just these two block forms like that. So if you have a symplectic structure, well, a symplectic structure is a skew 2 form on the tangent bundle, but that can be written as a map from the tangent bundle to the cotangent bundle. So you would take a vector, you take the interior product of the vector with the skew 2 form, and it gives you a 1 form. So omega here is a map from the tangent to cotangent, so sit in this block, and its inverse would sit in that block, from cotangent to the tangent bundle. So again, it's block, in this case we get block form, but in this case the zeros are along the diagonal part, non-zero terms. So to summarize this, both complex structures and symplectic structures give examples of generalized complex structures. And so therefore generalized complex geometry is kind of a broader kind of geometry that incorporates both complex and symplectic geometry. This was introduced to try to find explanations for mirror symmetry, which was discovered in string theory, and it found that, so string theory was a sort of mirror symmetry is a sort of unexpected symmetry between complex and symplectic geometry. Generalized complex geometry shows that in fact you can sort of unify them into a more general thing. Okay, so the next thing to ask about is what kind of generalized twistor spaces do you have? So spaces that encode a family of generalized complex structures. And so I want to look at these for these kinds of Quaternionic spaces. So for hyperkahler geometry, you have the global IJK, the global complex structures. And so each of those complex structures gives you a generalized complex structure. But you also have a hyperkahler metric, and it has the triple of Kahler forms, omega I, omega J, omega K. So each of those are a symplectic structure. And as I said, each symplectic structure also gives you a generalized complex structure. So now you have two families characterized by S2 giving generalized complex structures on a hyperkahler manifold. And in fact, there are other generalized complex structures on here that sort of blend both of those. So you actually get a whole S2 cross S2 family of generalized complex structures on a hyperkahler manifold. And so what I showed with my student, Becca Glover, is that you can put all of these generalized complex structures together into a single generalized complex structure on this space, this Z, which is the product of M plus S2 plus S2. So all of the generalized complex geometry, the whole family of structures are encoded in a single structure on that bigger space. And this is interesting because, I mean, the first examples of generalized complex manifolds were these ones coming from complex manifolds and symplectic manifolds, whereas this example sort of blends the two together. It's, if you look at the fibers of the manifold here, then some of the fibers are complex manifolds, some of them are symplectic manifolds. It sort of combines all of those into a single space. Okay, so that's how it goes for hyperkahler manifolds, which is one of the four kinds of Quaternionic geometries. The next thing we wanted to look at is Quaternion Kahler geometry. So Quaternionic Kahler geometry, so as I said, you have these local, almost complex structures, I, J, K. If they were covariantly constant, they would be complex structures, not just almost complex structures. But they're not covariantly constant. Their derivatives are given by, there's some expression like this. So what that means is that as you move around, as you move I, it's changing in the J and K directions as well. There's some sort of rotation of, so I, J, and K sort of start blending into each other as you move around. And what Andrew Sawon showed is that you can, over your Quaternion Kahler manifold M, there's another manifold dimension 4 larger, which is a bundle over that, and that M prime has a natural hyperkahler structure on it. So the idea is that on M, as you move around, I, J, and K get sort of twisted around with each other. And you sort of undo that twisting by adding this additional direction. And in the additional direction of twisting, there's a sort of reverse twisting that sort of counteracts it. Anyway, the result is that you get a hyperkahler manifold M prime from your Quaternion Kahler manifold. And so the sort of simplest example is just the Quaternionic projective space. In that case, M prime is just the Quaternionic vector space of one dimension higher, which, if you remove the origin from that and quotient by the H star action, you get down to the projective space. So this has a natural hyperkahler structure, and that descends down to the Quaternion Kahler structure on the end. So something I've been thinking about recently is still work in progress, is to use this Sawon's construction and our construction of generalized twistor spaces with hyperkahler manifolds to construct a generalized twistor space for Quaternion Kahler manifold. So we have, if this is our Quaternion Kahler manifold, we have the Sawon's construction gives us this hyperkahler manifold, and we know how to construct the generalized twistor space for that one. And so then I think if you quotient this by the H star action, if you get a space over here, that would be the generalized twistor space of the Quaternion pair. Okay, so that's kind of work in progress, but so that would be the next of the 4 Quaternion pair manifolds. And then, so if we go back, these 4 kinds of, so we've done this case, hyperkahler manifolds, and what I explained should work in this case, but then we still have this column. All of these have twistor spaces. The question is, do they all have generalized twistor spaces? And so we still don't know how to approach these cases. There's been various other work on twistor theory for generalized complex structures. In these cases, in those other 2 cases, Quaternion and hypercomplex manifolds, some people have looked at generalized twistor spaces where you just look at an S2 family of generalized complex structures. But I think there should be this larger family, this S2 plus S2 in those cases as well. But that's something that still needs to be explored. Okay, thank you for your time.
Yes.
Yeah.
Early on, you had a theorem from 3 people. I'm not sure I understood it. It sounded like you were saying if there was a locally quaternionic manifold, then the twistor space was globally complex, and the leap from local to global.
This there?
No, it was a
the other one.
Yeah, sorry, 3 French people. Yeah.
Yeah, these, yeah.
So you started with something that was just locally quaternionic, and then you took a twistor space, and it was complex, which means globally, right? Then that's.
Well, when I say local, I mean at each point there are local.
Yeah.
At each point you have local
right.
IJK.
Right.
So anywhere on the manifold, at that point there's local ones. And I mean that's the thing, they fit together. I mean there's a little more to, even in the case where they're out metrics, there's still a connection, a torsion-free connection that preserves the local. Well, it doesn't preserve there's a torsion-free connection that there's some compatibility with the Quaternionic structure.
But it becomes globally complex, the twistor space?
The twistor spaces, yeah. You have the local, almost complex structures combined into a structure on the twistor space, and then you get a global complex structure.
That just counterintuitive to me. Without any global condition, you get the global.
The global condition, I think, is coming from the compatibility with the connection. There's a global connection that has a compatibility with the local, almost complex structures. So they're not completely arbitrary. The local things are not. There's still some compatibility.
Any other questions? Thanks, speaker. What's more? So next one is in 5 minutes, and speakers here set the slides up.
I mean, I've only ever seen, it's obviously just the other thing, but I've only ever seen people talk about twistors in the context of mathematical physics somehow.
Yeah,
general relativity.
I don't even mention Penrose.
Well, okay, so yeah, I think he created it hoping to get quantum gravity out of it.
Yeah,
So
yeah,
I was just going to, is there a physical consequence of knowing that something that
having the twistor space?
yeah, suppose you knew it had a twistor space, but suppose you know it's quaternionic. Does that mean anything physically?
I think the reason that, I mean, a lot of these quaternionic spaces arise in physics. They're like moduli spaces and syntons and things like that. How do they use the twistor space? I'm not sure how they use it. There's probably some physical meaning of what.
You showed that given some assumptions, it arises naturally, right? Certain dimensions, starting to make a couple assumptions, and then you've got quaternions. So I guess they'd arise. But if you told that to a physicist, would they say, "Oh, well, that means"?
Oh, I think in most cases, quaternionic structure comes from supersymmetries in physics. We're looking at supersymmetric.
Okay, so supersymmetry, I think, bosons and fermions.
Yeah.
So there's something fermionic.
It's like interchanging bosons with fermions and vice versa.
So I don't.
Some sort of symmetry that interchanges.
So I don't intuitively have a connection between that and Quaternions yet, but maybe I should look into it. Cool. Thanks.
Yeah. In answer to your other question, though, like if you look at like for Quaternionic projective space, the reason that the Quaternionic structure there doesn't extend. There's no global complex structure on that.
That's fine.
Yeah, it's strange. Like you would think that would be an obvious Quaternion
Yeah, it
manifold.
seems like it.
So that's why it's Quaternionic Kahler, but it's not hypercomplex.
Okay.
You have local IJK because I forget exactly how to explain it, but it's something about sort of. It's from the non-commutative. I mean, you want to act.
Okay.
You sort of. I think you're quotienting by each. You take the Quaternionic vector space. You quotient on one side by each star, and then the complex structure is coming from the acting on the other side. But somehow it doesn't.
Yeah.
I don't know. I'd have to
I
go through the calculation, but.
I feel that makes sense.
Yeah, so it doesn't, like, so for example, like HP1 is S4. S4 doesn't have a complex structure. Only S2 has a complex structure, and S6 has an almost complex structure. S4 doesn't have a complex structure, but it's Quaternionic, so, but the Quaternionic structure is only local. It's the first sort of counterintuitive thing we learn in Quaternionic geometry.
Thank you.
Is this the mouth in Manhattan? Yeah, sure is. Exactly.
Excuse me, Dr. Sawon. Hi, I'm Alex Foster. I'm an applicant in your for the PhD program. I just wanted to introduce myself. We actually met once over the summer. I was in the UNC Greensboro REU, and we had come over one day.
Oh, you wanted to guys come over? That's right, yeah.
Yes, just wanted to, say hello and say I enjoyed the talk.
Are you interested in like apartments?
No, pure math.
Pure math?
Yes.
Okay. Are you presenting? Or you have a poster?
Yeah, I have a poster.
A poster?
Yep, if you come to the poster presentation, look for me. I'll be there. It's Friday. Nice to meet you.
Our next speaker is Joe Quinn. Joe will tell us something about Macfarlane hyperbolic three manifolds. Welcome.
Thank you. And I want to thank the organizers for inviting me to speak. I also want to apologize for coming late. I've been to see the talks this morning, but I'm actually pretty sick. I've got an empty cold, so I want to stay away from it. So yeah, I'm currently at the National Museum of Math, but this research is from my thesis in the Graduate Center in CUNY, and it's because of the UNAM in Mexico that I had the time to refine it and get it published and all that. So, as everyone here probably knows, Hamilton invented the Quaternions back in 1843. The parts that are most relevant for this talk are, first of all, that we can think of the Quaternions as an algebra over real numbers, right? That's generated by one I, J, and K with those multiplication rules. The other thing that's important is that these were largely geometrically motivated, that Hamilton was really looking for something that does for 3 space what the complex numbers do for R2. Found that you need 4 dimensions in order to do something similar. But that you do get this structure, this rotation of rotations on R3, where the unit Quaternions up to sign act on pure Quaternions, like SO3. Right? Now, something that's a little lesser known, I think, unless you're into this particular type of number theory, is what Leonard Dixon did in the 19-teens through 1924, which was generalizing Quaternion algebras. His motivation was really to study Diophantine equations. So the Quaternions give a really elegant solution to the 4 squares problem. There was already a solution to that, but the Quaternions make it a lot nicer and shorter. And so he was interested in studying other types of Diophantine equations. And so what he did is he said, okay, so the field that we're over doesn't have to be the real numbers, it can be any field. We're going to focus on the case of characteristic, not 2, but he did it for any field. And you also alter the multiplication rules, where now I and j can square to any non-zero element of the field. We retain the anti-commutativity of I and j. Ij is negative ji, and we just kind of drop k and write that as I times j in this theory. And you get a Quaternion algebra, which is denoted by a Hilbert symbol, and you just specify the 3 things you need to know. What's A, what's B, and what is the field. So it turns out that a Quaternion algebra like this is isomorphic to the 2x2 matrices over that field, precisely when there's a solution to that equation, ax squared plus by squared equals 1, over any xy in the field. When there isn't a solution to that, you get a division algebra, which is like what Hamilton's Quaternions are, right? Everything has an inverse. In a matrix algebra, there are things that don't have an inverse. If you really want to get into the nitty-gritty of it and find out, fully classify all of the Quaternion algebras over a field, you have to look at the ramification set. So that's something I don't really have time to go into too much detail here, but it's essentially a set of places of K, if you know what that means, where the Quaternion algebra has division. So basically, there are 2 Quaternion algebras are isomorphic if they're over the same field and they have the same ramification set. So for some examples, we have, Hamilton's Quaternions, that's where A and B are -1 and the field is the real numbers. And the only other Quaternion algebra over the real numbers is the matrix algebra. And basically, if either A and B or B is positive, then you're going to get the matrix algebra just because the real numbers have square roots of everything except negatives, right? But if I look at over the complex numbers, if I take that as my field, then I only have the matrix algebra because, well, everything has a square root. Things get very interesting in the case where the field is a number field, in other words, a finite degree extension to rational numbers. In that case, I have my matrix algebra and I have infinitely many division algebras. Some values of A and B will give me the same algebra, but I still get infinitely many isomorphism classes. Now, speeding ahead quite a bit to the late 1980s up till fairly recently, the work of McLaughlin and Reed, they have a great book called The Arithmetic of Hyperbolic Manifolds. And this is really extending what Takeuchi did for Fushkin groups and surfaces starting in the late 70s. So we're looking at non-elementary finite volume hyperbolic manifolds. So from now on, whenever I say hyperbolic manifold, we mean non-elementary finite volume. Its fundamental group is isomorphic to a Kleinian group, which is a discrete subgroup of PSL2C, right? And so what we can do is form the trace field of the group, which is just take the trace of everything in the group and extend the rational numbers by that. And we can form the Quaternion algebra of the group, which is just linear combinations over elements of the group with coefficients from the trace field. So in dimension 3, we have this great thing called Maass rigidity, right, where Our isomorphism classes of our groups are just given by conjugation. And so, due to that, the trace field is always a number field. And so I put concrete number field, and so this is kind of a subtle point. So it means not just a number field up to isomorphism, but actually a fixed number field with a fixed embedding into C. The Quaternion algebra of the group is a Quaternion algebra in the sense of Dixon. Not only that, but both of these things are manifold invariants. Now, in the work of McLaughlin and Reed, they're actually more interested in something else called the invariant Quaternion algebra and invariant trace field. This is what you get when you do the same thing using the group generated by squares in the group. I'm actually going to be more interested in the ordinary trace field of Quaternion algebra. But if you do that, you get commensurability invariance. Some properties of this are that if the group is non-co-compact, in other words, the manifold is non-compact, then the Quaternion algebra is a matrix algebra. In the case where the group is co-compact and arithmetic, the Quaternion algebra is a division algebra. And so, right here I'm talking about the invariant Quaternion algebra. If I want to say something about the ordinary Quaternion algebra, well, it happens that I can find a finite cover that has those same properties. Okay, so I had read all of that when I was a PhD student, and my reaction to it was basically like, well, okay, what Hamilton did was geometrically motivated, right? He wanted to find this structure on R3 similar to what the complex numbers did for the plane. However, these generalized Quaternion algebras are entirely from number theory. They're arithmetic objects. However, we're seeing them come up in applications to hyperbolic three manifolds being used to classify the manifolds. And there isn't really a geometric interpretation for a generalized Quaternion algebra. It's not even really talked about. One caveat is that there are some cases where you get geometric interpretations in the case where the Quaternion algebra admits an embedding into those Quaternions, and then we're just using the geometry that we already know about from H. But what I really wanted to know is this: can we generalize the geometric properties of H to something similar for Quaternion algebras over number fields, and use that to study hyperbolic three manifolds, right? Use the one to study the ones that the three manifolds that the Quaternion algebras are associated with. The answer is sometimes, but for a kind of interesting class of manifolds, I think. So, as I was digging into the research about this, I found this guy, Macfarlane, who was writing in the late 1800s. And he came after Hamilton, but before Dixon. And he was interested in something called hyperbolic Quaternions, a term that he came up with. And he was experimenting with changing the multiplication rules of the Quaternions to see if you could get something for hyperbolic space. And so, essentially, he was looking at what happens if ijk all squared a positive 1 instead of negative 1. And this drawing right there is from a paper from 1891, or actually it may be the one from 1900, I don't remember it. I think it's 1900, yeah. That's basically Minkowski space, and we're seeing like light-like vectors, time-like vectors, and a light cone, but 17 years before Minkowski. So that's pretty interesting. And it's also really promising for possible applications of these other Quaternion algebras. So why wasn't Macfarlane better known? Well, around that time there was a lot of debate over what's going to be the notation moving forward for vectors. You have like ij and k ended up making it into Calc 3 for the coordinate axes of R3, but there's no mention of the origin from the Quaternions. So there's a lot of sort of like borrowing and cutting and pasting things together, and admittedly Macfarlane's notation is kind of atrocious. It's really difficult to read. His ideas are awesome, but like he just made up his new names for hyperbolic trigonometric functions, and it's pretty dense to read. Also, there was some algebraic inconsistencies in his first paper on this that were resolved in the second one. So anyway, there's this quote by Macfarlane that I just found very inspiring. I'm convinced that the notation can be improved, the principles required to be corrected and extended, that there is a more complete algebra that unifies Quaternions, Grassmann's method, and determinants, and applies to physical quantities in space. The guiding idea of this paper is generalization. What is sought for is an algebra that will apply directly to physical quantities, will include and unify the several branches of analysis, and when specialized, will become ordinary algebra. So at that point, I felt like I'm basically collaborating with this guy who died over 100 years ago. And moving forward into my my thesis, luckily my advisor gave me the okay to continue with the project. And so after some work, I found that the best way to unify all these different ideas, Macfarlane, Dixon, Hamilton, is in the language of involutions. Okay, so you can define an involution over any algebra. We're just going to focus on the case where the algebra is a Quaternion algebra, that's all we need. So in that case, an involution is just some function on the algebra where it fixes the identity. If you do it twice, you get back to where you started, and if you do it to a product, it switches the order and involutes each of the things. We define the symmetric set of the algebra with respect to the involution as the things that are fixed by the involution, and the skew symmetric set of the things that are negated by the involution. We call the involution standard when anytime I multiply a thing by its involuted version, I get something in the field, and the symmetric set is the field. Okay? So, let's take some arbitrary Quaternion Q written like so. The standard involution is unique in this case, and it is the Quaternion conjugation, where you negate the imaginary part. We also define the trace, which is the Quaternion plus the involution of the Quaternion, which is just twice the scalar part. This actually agrees with the matrix trace under any matrix representation. And we define the norm as the Quaternion times the involution of that Quaternion. That agrees with the determinant under any matrix representation. All right, so in general, I'm going to use subscripts to indicate restrictions on the trace and superscripts to indicate restrictions on the norm. All right, so S sub 0 is the pure Quaternions. S to the 1 is norm 1 Quaternions. All right, so now finally I can state what the main result is. First of all, using that notation, we can write Hamilton's theorem from 1843 in this sort of weird way, right? So when I talked about the pure Quaternions and then the norm 1 pure Quaternions, that's basically the sphere, right, that Hamilton's Quaternions are acting on. I can just call that the skew symmetric elements with norm 1. And then PH1 is as it usually is, so it's the norm 1 Quaternions up to the sign. And I act on it by conjugation, as like so. Okay, so now definition. And this definition and the theorem had to sort of go back and forth with each other. They're almost, the definition is almost as important as the theorem, I think. So we call a hyperbolic three-manifold with Kleinian group gamma Macfarlane when its trace field is an imaginary quadratic extension of a real field. And the non-trivial element of the Galois group of the trace field over the field acts freely on the ramification set. So what I mean by acts freely is it fixes, it doesn't fix anything, right? And it acts on it. So it doesn't send a place to something that's not ramified. Okay. Another thing here is that when I say a real field, I don't mean a totally real field. So usually in the theory of arithmetic hyperbolic three manifolds, you're talking about all embeddings of the field are real. In this case, it doesn't matter, just the concrete field has to be real. All right, and then we get a theorem, and we see that, all right, so if my manifold is Macfarlane, then I can find some involution. It's not the standard involution, it's this other involution, such that the action of the fundamental group is spatially represented like so. And as you can see, it looks pretty similar to Hamilton's theorem if you write it in this sort of strange way. Instead of skew symmetric elements, we're taking the symmetric elements. So over here we have norm 1 to give us the sphere in R3. Over here we have norm 1 and then positive trace. What that's doing is it's giving us a hyperboloid of 2 sheets and then taking the upper sheet. So it's just a hyperboloid model for hyperbolic 3 space, but defined over the real part of the trace field. Now, I probably won't have time to do the proof, so maybe I can come back to that later if I do. I think maybe more important is to talk about the diversity of Macfarlane manifolds, right? So, okay, so we have this nice theorem, but how often is a manifold actually Macfarlane? Well, it so happens that if I have an arithmetic and non-compact manifold, it's always going to be finitely covered by a Macfarlane manifold. If I have an arithmetic and compact manifold that contains an immersed totally geodesic surface, again, it's finitely covered by a Macfarlane manifold. And if I have a non-arithmetic manifold, then I have infinitely many commensurability classes in each category of compact and non-compact. So this is something that's somewhat unusual in the theory of hyperbolic 3 manifolds, that you have a property that applies to every single type of combination of arithmetic, non-arithmetic, compact, non-compact. And we have some examples down there. Okay, so with this machinery, if you really want to convince people that what you did is useful, you have to do something that they couldn't do before you had it. So, so the application is fundamental domains. So we have a Macfarlane manifold, and what I do is I define the symmetric space with respect to involution as M for Macfarlane space, and then define I sub gamma as the algebraic hyperboloid model for gamma. So that's the thing that I just described. You take positive trace, norm 1, it's a hyperboloid model over the field. Now, right, this is an important point. If I really wanted a hyperboloid model for hyperbolic 3 space, I would have to tensor up to R before I took my norm 1 positive trace. But don't do that. If you do that, you lose the whole point. Not by not doing that and acting my group on it, I can actually realize all of my orbit points using algebraic numbers. And so in this way, we consider the Dirichlet domain for the action of gamma on its hyperboloid model. And so the Dirichlet domain is a connected fundamental domain with phase pairings given by some finite set of generators for gamma. That's what a Dirichlet domain always is. But we have this interesting thing now where both the group and the hyperboloid model for the group are both embedded inside the same Quaternion algebra, and we have the same sort of duality that we have with Hamilton's Quaternions. In particular, I can look at a point on the hyperboloid model and think of it as an isometry. What does it do? Well, it actually is a translation along the geodesic that passes through that point N1 that takes gamma to gamma squared. So 1 is 1, so that's nice. The trace is always twice the height. This gives me sort of a systematic way of looking for sides as I go up my hyperboloid. That's the thing that I just said. The point on the hyperboloid translates along that geodesic. And also, I can sort of project these geodesics down onto the pure Quaternions inside the Macfarlane space and get something like a slope to keep track of which direction they're going in. And that gives me a nice way of avoiding repetition as I'm looking for sides, or avoiding looking for sides where I've already found one that's closer. And so it really shortens the algorithm for finding a Dirichlet domain. In the case where the group is closed under the involution, then the orbit of 1 is actually contained in the intersection of the group with its hyperboloid model. And so This is something I didn't actually use, but always wanted to. Like, you have the symmetric space, there's also the skew symmetric space, and you have an equivalent way of classifying points by their location in the skew symmetric space on a hyperboloid of one sheet. It turns out there are loxodromic elements that rotate by pi over 2. So that's kind of something I always wanted to come back to and see if I can do more with, but so far I haven't. This is an example of a computation of fundamental domain for the Whitehead length complement, done like mostly by hand, which would be nearly impossible, I think, with the previous methods. And then this is one for the hyperbolic punctured torus. You have similar methods that work for surfaces, particularly subsurfaces and manifolds. And I think I'm about out of time. Thank you.
Questions? Any questions? No. So maybe I just wanted to ask one. So part of what I'm going to say is very similar to what you said, except you're working in three-dimensional space while I'm still just in two-dimensional space. Have you thought about kind of the connections between the non-co-compact and the compact groups in this context? So meaning like you act on the space by those groups, and you kind of look at sort of functions on the respective spaces and see whether or not there are any kind of correspondences between the spectra.
Like between the compact and non-compact.
Yeah.
I guess I don't think so. I mean, I think one thing that this method does is So ordinarily, if you're looking at non-compact manifolds, you have cusps which are identified with points on the boundary, right? And if you're in the upper half space model, those points are very accessible for these complex numbers. When you're using the hyperboloid model, those points, instead of being, well, there's still points on the boundary, but instead of thinking them as complex numbers, you sort of thinking them as points at the end of a line, right, as it goes up the hyperboloid. So it sort of interchanges the accessibility of the cusp points with the points within the manifold. But one thing that's nice is that you can think of the pure Quaternions as pointing to the cusps. I don't know if that answers your question.
Certainly. Maybe it'll be evident.
Okay, because we're going to introduce.
Sure.
Yeah, okay.
It's okay. I'll put it.
Okay, thank you. Yeah.
So can we thank the speaker once more?
Thank you so much, Quinn, and thank you very, very much for your work on Macfarlane's hyperbolic free manifolds, right? Okay, fabulous. Okay. Hey, hi, how are you? I am Johannes Hamilton. Okay. And I'm sorry the friends couldn't be here. They said they had to teach.
Oh, yes, yeah.
And
It's not as convenient that way on the other.
yeah, I tried.
I have plenty of them.
I figured that out because last time I said, oh, I'm sure about it. Sawon control. I said, he's going to be my advisor, which if we were here, I got him yesterday. He said, I have too much to deal with all this stuff.
Yeah.
Right? So but he told me to tell him below.
Okay.
So this is my friend Terrence Blackman, and he's going to be, it's really wonderful to. Oh, Terrence, are we ready?
Yeah, we start at 3.
Oh,
so we have
that's
a few
fine.
minutes. I just thought I'd pop it up real quick.
Just so glad to meet you.
Give her a moment.
Thomas Hamilton.
That's what yeah, I did an elementary thing with Maxwell's equations. I hope it doesn't hold like yours.
I think I write Maxwell's equations.
Okay, well, I actually know hyperbolic using the other stuff.
Yeah.
I went through all the details. Hitchin and I, we went through all the details.
Okay.
And, you know, the lawyer went through all the terms and everything. It was,
Okay.
really working on that because I'm physics. So I do have physics background too, and I have math background.
Okay.
My math background is
You know that my father was a mathematician.
yes, I do. I hear about that. Oh my gosh. Wow. So you know that a lot. Oh, really? I was able to go to the airfield.
Just came from Brazil in July. And a week line.
I was in Brazil in August, actually, for the ICO. Okay, so.
Yeah, we can.
Okay, good stuff. I'd like to introduce to you a good colleague of mine, Terrence Blackman, and he's going to speak on spatial correspondences with Maass, waveforms, and Quaternion groups. And let's give him a hand to start him out. Great.
So,
Okay. Go for it, Terrence.
So funny. It's a wonderful pleasure. So thanks, Janice. It's a pleasure to give this talk. I've been, working on this stuff for some time, and it's always, really a privilege to be a part of the panel. This talk today is really about the arithmetic and geometry of Quaternion algebras. It's sort of very similar to what Quinn just talked about, but with some different aspects. So, and I want to talk about some aspects of spectral theory of automorphic Laplacians. So this work is sort of part of a paper that was published in the journal Number Theory maybe a year or so ago. And in it, what we describe sort of explicitly some new spectral correspondences between spaces of Maass waveforms on the unit group of a Quaternion algebra and spaces of Maass forms on a kind of nicely related congruent subgroup of the modular group. These correspondences are predicted by the Jacquet-Langlands correspondence. And I should say that this is work that was done jointly with Stefan Lemural at the University of Göteborg, Chalmers in Sweden. And I've sort of put this title, kind of, why is n gamma 012 nu lambda of Kuchenbach type? Because in a way, this is the question that sort of motivated the work. And it's still an unanswered question. And so I'll give you some broad sense of what we've done. I should say you know, I'm going to not try to rush and get to some destination. I'm going to sort of try to go in as leisurely a fashion as I can, and you know, allow myself a little luxury of pausing and looking around, and you know, so you know, mathematics shouldn't just be about getting to a destination. So there we are. Now, the other thing that I always like to say is that, you know, I've spent 25 years of my life at a very small college called Medgar Evers College in Brooklyn, and so whenever I have an opportunity to speak, I always want to say something about Medgar Evers College. It's located, I now serve as the dean of our School of Science, and so I was very proud to say something about our college. So it's established in 1969. It's named after our famed sort of civil rights leader, Medgar Evers, and it's part of Central Brooklyn community, and you know, it's a senior college in the City University of New York system. And then finally, you know, what we do here is we try to do some research that often is a little, you know, it's, you know, I have to be a booster for a place. We tend to do some research that often kind of really attempts to address some of the challenges that we see in developing kind of mathematicians in underrepresented communities. And so we think that if you do that, then you ought to spend some time thinking about research. And so in that vein, let me just say a little about what I try to do. So the plan is, you know, a kind of outline of the basic ideas, a sense of what we proved, and maybe an outline of the proof. Depends on how far we get, perhaps some, you know, I'll at least give some sense of what the idea in affecting the proof in this context looks like. So I want to start off just kind of jumping right into it, and then some of the definitions that were made earlier will work in this context, and so I'll perhaps say some of them, but I just want to kind of jump into, you know, what the problem was, and then I'll spool things back. So there's this work kind of emerged from a paper by a guy named Morten Riesager, and Riesager is sort of investigating sort of the asymptotic behavior of a spectral counting function for Laplace eigenvalues for Maass new forms on gamma 0 n. And he sort of asks the question sort of for which Hecke-congruence groups gamma 0 n is this spectral function of co-compact type. And this notion of co-compact appeared in the talk that we listened to earlier. So the idea is that gamma is a cofinite arithmetic Fuchsian group, and a little later I can define what these things are, but I think we saw some of the definitions in the talk earlier. So gamma C, meaning gamma co-compact, gamma NC, non-co-compact, but cofinite. So the idea is going to be that the co-compact gamma is going to come from so I'm going to take an order in a Quaternion algebra, and then I'm going to take the group of units in the order, and that, it turns out, gives rise to a kind of co-compact arithmetic Fuchsian group. Now, associated with an order, there's going to be a notion of discriminant of the order, and so it's just some number d, and then I'm going to just simply form the Hecke-congruence group gamma 0d, and essentially what I'm going to sort of somehow show is that, or at least what we've proved is, I'm going to look at functions on h mod gamma mod O1 and h mod gamma NC, and sort of establish some correspondences between the spectra associated with those functions. Right? So gamma, cofinite arithmetic Fuchsian group, del gamma, the automorphic Laplacian related to gamma, and gamma lambda, sort of the number of lambda less than or equal to lambda, is part of the spectrum of delta gamma, and here's a corresponding spectral counting function. Now, it turns out that, you know, when we look at n, lambda sort of associated with the co-compact, it has an asymptotic expansion of the form sort of volume O1 mod h over 4 pi, and then something that is of the order of the square root of lambda over log lambda. When we look at the asymptotic expansion of the Hecke, sort of spectral complete function related to the Hecke congruence group, then it has sort of very similar sort of things on the first term, but then it has an error term that is of the order of the square root of lambda, sort of log lambda. And so I, just draw your attention to it, because this is going to be critical. Right? So in a way, the association is that if we have a co-compact group, then what we have is an error term that is of the order of the square root of lambda over log lambda. And if we have a Hecke congruence group, sort of non-co-compact but cofinite group, then we have an error term that is of the order of the square root of lambda times log. What Riesager does is he defines sort of a spectral counting function that only counts the new forms on the Hecke congruence. The idea of new forms is just to simply think of I have a set of forms in a group. I have a subgroup. There are a set of forms that descend to the subgroup that are intrinsically new to the subgroup, and those are the ones that we refer to as sort of new forms, right? So he defines a sort of counting function which counts only the eigenvalues corresponding to the new forms in gamma 0D. And what he discovers is that when D is a product of an even number of different primes, that voila, the error term looks very much like the error term in the co-compact situation. And so then the question becomes, so this constant is something that's sort of sitting in between 0 and 1. And so what we see is that this spectral counting function for new forms has an asymptotic expansion that is sort of characteristic of what you would find in the sort of co-compact case. And so the question became sort of like, how do you explain this? And moreover, are there other values for D, not a product of an even number of different primes, which give rise to an asymptotic expansion that looks like that? Okay, so the question, are there other values for D for which n gamma 0D new lambdas of this form? And it turns out Riesager answers this question with a really nice theorem. So if we let sort of m and t be natural numbers defined in the following way, so m is nt squared, and you can kind of begin to get a sense of why gamma 012 was of some importance, right? Then this spectral counting function for new forms is of co-compact type, if and only if at least one of the following. So n contains at least 2 primes, and n is a prime, and 4 exactly divides it. So these are our, so I started here. In this context, you can immediately observe that, say, in a way concretely, this means that if you look at sort of m gamma 0 pq, where p and q are primes new, that one gives rise to, if you look at m gamma 0 4p new, then that one also gives rise to. And so in that context, we can see that gamma 012, the question that I started with, is one where we have a spectral counting function for Maass new forms that are of the spectral counting function for Maass new forms, which is of co-compact type, and the issue is there something interesting about gamma 012 that gives rise to that? Well, it turns out that so I've already said this, or there's spectral correspondences which explain the theorem, and how is it explained? Well, it turns out that this is all based in a very nice sort of result that is part of the work of the Jacquet-Langlands correspondences. So it turns out it's well known that correspondences between spaces of automorphic forms for compact and non-compact arithmetic function groups These are explained by Jacquet-Langlands. Jacquet-Langlands correspondence asserts that you have such a correspondence. And what it says is that, to any non-constant eigenfunction of Laplacian on a co-compact arithmetic Fuchsian group, there corresponds non-trivial plus form, same eigenvalues on some non-co-compact but co-finite arithmetic Fuchsian group. And this is the essential statement of Jacquet-Langlands correspondence in this context. You see, and in some sense, this is the, this is the sort of import of the work, right? So everyone broadly knows that this correspondence exists. However, the question is, which co-compact arithmetic Fuchsian group corresponds to which non-trivial cusp form? And this is essentially what we've answered in this paper, or at least what we've answered in some small measure in this paper. Kind of like having two big piles of drums and knowing that one drum in this pile these piles are related, but not knowing specifically which drum in this pile is related to that drum in that pile. And we've been able to establish the ways in which we can say which drums are linked to which others. So the basic sort of outline, and this is where the talk kind of is associated with the business of Quaternion algebras. So what we start with is a Quaternion algebra over Q, and those definitions were in the earlier talk. And then what I do is I take an order in the Quaternion algebra, a general sense. This order has some discriminant B, and what we look at is sort of the group of units in that order, and then sort of the associated gamma 0D. And so we have this really nice way of starting with a Quaternion algebra and kind of ending up with two arithmetic Fuchsian groups, one which is co-compact, and the other which is non-co-compact but co-finite. And then I want to look at sort of the spaces that are formed when I sort of act on the upper half plane with these groups. And then I want to look at the space of sort of L2 functions, the space of L2 functions on these surfaces. And this was a question that I was sort of asking in your case in the three-dimensional world. Is it possible to think of, rather than thinking of a kind of Fuchsian group, are there some sort of Kleinian groups which act in this way that potentially one can look at sort of functions on these spaces and ask a similar kind of spectral question. So to kind of say that once more. So O1 group of units in an arbitrary order with discriminant D, indefinite rational division Quaternion algebra, gamma 0D, the Hecke congruence group, and the definitions for a Quaternion algebra of a field F, central simple algebra, and so on, were said in the previous talk, so I won't repeat it. So how have I been able to sort of explain? So these are our results. So essentially, in the case when we can think of n as a product of an even number of primes, so remember, so Riesager has this sort of m is nt squared. So I'll just pop this back real quick. So Riesager sort of says that the spectral counting functions for new forms is of co-compact type if I take m to be nt squared like this, and n contains at least 2 primes. So I started off with just thinking of t squared as being 1 and n just being 2 primes. And if you do that, what we quickly discover is that if I take O1 to be the unit group in a maximal order in an indefinite rational Quaternion algebra, and I take sort of the discriminant d of a to be 1, then this is actually described by the work of Ström, and Bolt, and Johansson, and essentially what you can establish is sort of a bijection between the group of units that come from the maximal order in this Quaternion algebra and the Hecke-Converse group that is derived from the discriminant, and it's an exact sort of correspondence between the spectra. The second case, what I looked at was a situation where so you see essentially the game is, I know what I need n to look like, and really it's just a question of sort of figuring out what kinds of orders will satisfy, what sort of unit groups coming from orders will satisfy will satisfy the relationship that I'm looking for. So in the second case, if I take t squared to not be 1, but I want to take n and t squared to be relatively prime. So essentially, what I want to take is I want to take sort of the group of units. So the theorem is if I take O1 to be a unit group in an Eichler order of level t squared in a maximum order with the discriminant n, then once again I can find a correspondence between the eigenspace of delta O1 and delta gamma 0 m, where m is nt squared. So again, this is all still kind of work of Stromberson and Riesager. And then the third case, that's sort of what we did was to sort of take sort of n to be p and q, where p and q are primes, and here we were able to sort of use the Selberg trace formula to show that, once again we have this equivalence of the positive Laplace eigenvalues, including multiplicities for Maass forms, and here so I have sort of O1 PQ P2R Q. So this is sort of something that is of index p to the, so it's an order that is of index p to the 2r q to the 2s in an order with discriminant PQ, and we can attach to that a congruence group gamma 0 p to the 2r plus 1 q to the 2s plus 1, where r and s are sort of bigger than 1. And then we can show that the spaces of Maass forms on these two, the spaces of Maass forms on these, in this case, the co-compact, non-co-compact, co-finite, and in this case, the co-compact group actually correspond with each other. So the last sort of, there are some broad sort of changes, and so we were able to establish that if we take r to be a positive integer that is divisible by an even number of primes, and every prime dividing r does so to an odd power, and take u to be something that is a positive integer, sort of relatively prime to r, and we were able to establish that the positive Laplace eigenvalues, including multiplicities for Maass forms on O1 RU and gamma 0 RU, also coincide. And in a way, this captures almost all of the cases that are prescribed by Riesager's theorem, except it turns out, actually this is a nice corollary which allows us to sort of establish not only correspondences between the forms on co-compact and non-co-compact, but also correspondences between the forms on things that are co-compact themselves. I'll leave that for a moment. So what we still have not been able to do is to establish that, in the case where n is 4p u squared, p is a prime, and u is odd, there is still no Quaternion order with the natural correspondence between new forms as in the theorem. And so our conjecture is that, maybe there isn't one in this case for gamma 012. I haven't proved this yet, but at this point the conjecture is that for new forms in gamma 012, there is no natural Quaternion order that will establish that. So I went to skip. I sort of plugged this in just as a kind of way of giving some background. So this was, addressed in the earlier talk, and so I went to skip this also. This was just a way of giving giving a bit of history attached to it, and I wanted to get to the very end. I know I prepared way more than I needed, but soften is sometimes a good thing. So I want to get to the end. So the question is, how do we prove? And the idea is, so what does the strategy for proving? What does the strategy for proving this sort of looks like? And so essentially what we're doing are sort of comparisons via the Sawon choice formula. And there are a couple of ideas. Sort of what we want to show is kind of like a special linear combination of these gamma 0 RU trace formulas have the property that the sort of parabolic term vanishes, and then when we look at this, the identity term sort of area of the fundamental domain part of what we just described. The elliptic term and the hyperbolic terms all agree with the corresponding terms for an associated linear combination of the trace formulas for the co-compact group. And then there's sort of kind of an agreed, there's sort of a notion of some sort of local embedding numbers, and we want to see that those local embedding numbers, that there's agreement on these local factors, which will ultimately give us the correspondence. Just to give some kind of flavor, I tried to do like a special example, but maybe I'll just say generally. You know, some of you may or may not be familiar with the trace formula. So it's sort of a general identity which connects to sort of geometric and spectral terms. It's kind of an identity of the following forms: the sum overs of spectral terms, the sum overs of geometric terms. You know, the spectral terms come from discrete and continuous spectra of the automorphic hyperbolic Laplacian for the cofinite group. And the geometric terms are sort of integral operators which depend on the conjugates and classes of the group. And so essentially we take two versions of the Sawon trace formula, one for the co-compact groups and the other for the Hecke-congruence groups. The point is that it's hard and easy at the same time, because in a way the trace formulas for both of these types of Fuchsian groups are well known. You know, sort of broadly, the Sawon trace formula for the co-compact group sort of looks like this. Has an identity term, hyperbolic term, elliptic term, and what we do is we think of this as being kind of, you know, sort of written in this form. So term 1, term 2, term 3, you know, identity, elliptic, hyperbolic, and in a similar manner. I'm just going to go quickly for the Hecke-congruence groups. Essentially, what you have is an identity term, elliptic term, hyperbolic term, and then you have this parabolic term that's sitting on the end. And the essential game is to kind of find linear combinations of trace formulas of this type that essentially kind of zero out the parabolic term, and find an associated linear combination for the co-compact ones, so that when you filter them through, you essentially end up with a parabolic term going away and equality on the area term, equality on the elliptic term, and equality on the hyperbolic term. And in a way, this is broadly the structure. This is broadly the structure of the proof. So I suppose I've gotten to the place where perhaps I should stop. But you know, that's the sense of the game. Thank you. It's actually quite interesting. You know, when I first started doing it, you know, once I was able to figure some linear combinations that allowed for the area term, to kind of establish some kind of equality on the area term, it became clear to me that it had to be true. And I just spent lots of time just trying to figure out what were the associated sort of factors that I needed on the other parts of this. And it's really, broadly speaking, a counting problem. I know, I've used up your time. Yes.
So I think in the theorem you said that you wanted your two numbers to be product, but
Yes.
and then you had a conjecture that if it's a certain
Yeah, so if it's, it starts with, the question that Resager asks is, you know, why is n gamma 0 12 of co-compact type? And so what I'm claiming is that after I've spent a bit of time with this, is that the answer to it is that there is no, my conjecture is that there is no co-compact order that I can derive from a Quaternion algebra that will do that job. And I mean, I haven't proved it, but I'm quite convinced that there's nothing there. Yeah. I just want to go back a little bit. Yeah.
So, but there's other cases too, right? Like, so you have the theorem for.
So yeah, so I do have it for other cases, but for this particular case where I have 4 times prime and u squared, then I'm claiming that there is no Quaternion order with a natural correspondence between the new forms as in the theorem that we do. And so in particular, if I think of n as being 12, and then I'm thinking that gamma 0 12, the space, even though so Resager established that n gamma 0 12 nu lambda is of co-compact type, I'm claiming that I don't believe that we can find a co-compact arithmetic Fuchsian group to establish that correspondence. So somehow that's a co-compact type in and of itself, and there's some other thing that's operating there. Thank you. Did you have a question?
Yeah, very good. So actually, starting with the next. Yeah, okay, so this so in the following cases, the
Yeah. So in all of the cases, I'm working with an indefinite rational terminology. Because that's the one from which you derive the co-compact arithmetic function. Yes. Yeah, it's actually quite interesting. Yes.
Oh, okay, and so the meta quotient H
Yeah. So what you have is some space on which you can have functions, and so you look at the space about 2 functions, and then you look at the spectrum, and then you try to establish whether or not there's a correspondence between the spectrum. In order to establish correspondence between the spectrum, you need to use a subroutine formula, not directly, but some linear combination of subroutines. Yes. I just know that you're, he was very helpful to me at the very beginning. Who was a faculty member. No, not Szymanski. There's a recent, John Voigt. Yes. So this work actually began at, some years ago at Macfarlane College, and he was the person I called up and said, "Can you explain to me stuff about?" I read his thesis, and so can you explain these things to me about Quaternion algebras? Yes. Yes. I've been following the evolution of the book online. Thank you very much. I appreciate you coming in and listening to it. And say hello to Jonathan. And I'm sure he's here someplace. Yeah. Yes. Yeah, you could. you can use mine or you can use yours. It's no, that's fine. It's set up. We have yeah, we have and then we'll have a PC also. So you shouldn't. You can get it. So how has New York been for you? It's been good?
Yeah.
Yeah.
I mean, I'm from upstate.
Ah, so it's easy transition.
Yeah, and I went to the graduate center.
Oh, yeah, so I knew that. Yeah, I did my degree at the graduate center. Yeah, so some years ago.
Yeah. I miss Mexico.
You do. It's warmer there.
Yeah. There's been some talk about trying to get some kind of seminar.
I would love to do that on this Quaternion bit. You see, I think we can have like a, I think we can have like a Quaternion seminar at the graduate center. I would be absolutely, thrilled to be a part of it. And, perhaps we could, when I get back, I'll get these guys and see whether or not I can motivate them to push maybe. Yeah, I think it would be very useful.
Like, I don't really, at the museum, they don't really
have a chance to sort of work with our research. Yeah,
but
that's one of the challenges of, one of the challenges of jobs like that, where it's a great job, except that you have to, except that you have to work really hard to get any sort of research thing going.
Yeah. I think if you eventually.
Yeah, I mean, I don't know. I want to give you. If you, maybe initially you're interested just like in doing, in just teaching.
At the very least, though, if I would attend.
Yeah. Yeah, and so if we just have like a little, if we start with the seminar and then, maybe at some point you're thinking, perhaps I should teach something. Yeah, that would certainly be, something I think would be nice to figure out how to facilitate.
Yeah, it might be possible to do something after hours at the museum.
Yeah. So also, so that could be a place to have the seminar. It would be nice. It'd be a prevention. Folks would probably be happy not to go to the graduate center, go to the museum. Yeah.
Yeah. So we'll be in touch.
Okay. So we'll definitely be in touch.
Yeah. This cold didn't come at the worst time.
Yeah, I know. Chris was actually down. Yeah, he barely made it this morning. Yeah. I was worried because I drove from New York this morning.
I drove last night.
Yeah.
And I was just like drinking coffee, taking time.
Well, yeah, I should preemptively take something. Yeah, I have some pills in my. All right, we will. I'll see you soon. Let me just. Hello, how are you doing? speaking this afternoon?
Oh, no, but organize a session tomorrow. I just want to see what's the logistics here.
Oh, no, it's actually pretty simple. They have
What's
they have an HDMI cable, but then they have these two. They have these two.
I don't have HDMI.
No, but it's fine. You don't have to.
It's
They you can plug this one in, and then it has
Is
the
this stays
series.
with the room?
Yeah, this
Okay.
stays with the room. So it's been pretty easy.
Okay, yeah. As long as there is HDMI, my computer will work otherwise.
Yes, you got it.
All right. Thank you, sir.
Take care.
Have a
No
nice
problem.
conference.
You do the same.
Thank you.